Now we're going to be looking at the concept of symmetry. Remember that when we talk about transformations, we can talk about fixed points. Now, a fixed point is a point where its image is the same as the pre-image. Basically, it's a point that's not moved by the transformation. So if you think about a transformation applied to the entire plane, then we can talk about the fixed points of that transformation. Of course, the identity transformation fixes the entire plane. A translation on the other extreme, or a glide reflection, either one, move every point in the plane to something new. So there are no fixed points for translations and glide reflections. Reflections, mirrors, have the mirror line or axis of reflection as fixed points. Any points on the mirror line are going to be fixed. And so there's a whole infinitely many, but all in a straight line for the fixed points there. And then we talk about the fixed points of a rotation. The only one is the center of the rotation. So there we're talking about what's happening at the individual point level. But we can also restrict our attention to a specific set, as we often have, like a specific triangle or maybe other polygon or something, subgeometric figure, or a graph of something like a parabola, y equals x squared, or an angle, like y equals absolute value of x. And we can take that collective set of pre-image points collectively, and they get mapped collectively to some image set. So if we think of the restricting the domain of the transformation strictly to the points that are in that pre-image figure, then we're looking at the range figure is a incongruent figure if we're talking about an isometry, the set of image points. Now, if collectively those two sets of points are the same points, even though they may get moved around within the set, some of them or even all of them, then we say that the figure is symmetric with respect to that transformation. So it fixes not points individually, but it fixes the set of points. Not really fixes is not the right word. It just leaves those, it moves them around, but collectively they stay the same. So we can talk about, rotational symmetry, or we can talk about translational symmetry or reflective symmetry. So, of course, the rotational symmetry about the point, notice we can rotate around that point and get the same figure. Now, every figure has rotational symmetry about any point if the angle is a multiple of 2 pi, an integer multiple of 2 pi. In other words, a full circle rotation gets you right back where you started. It fixes actually every point. So in fact, that's actually the identity transformation. So if we sort of ignore that one, then talk about other types of rotational symmetry, then we can look at what the smallest angle is of that rotational symmetry. Let's call it alpha. Then any integer multiple of alpha is also going to give you an angle of rotation about the same center point that's going to give you symmetry as well, rotational symmetry with that one. Specifically, if the rotational symmetry about a point is 180 degree rotational symmetry, we say it's symmetric with respect to that point. So for example, if it's rotational symmetry of 180 degrees about the origin, we would say that has origin symmetry. Okay, we could have translational symmetry. Here's an example of something that has translational symmetry, and of course for this to happen you have to have a figure that's going to go on forever, because translations will always move points further out in the direction of the vector. So for example here, if we move say every point here in the original graph, which is not the axes but the wave, which is actually a sine wave here, and we move every point to the right by 2 pi, we get another point in the same set. Of course, the set has to go on forever for this to happen, not just what you see on the screen, but it goes on forever. We call translational symmetry like this, particularly when it's applied to a function, as we say the function is a periodic function. But that is a translational symmetry. Okay, and we can look at different types of figures and talk about what kind of symmetries they have. Now it turns out that I think probably because of our bodies have not true symmetry, but sort of a reflective symmetry about a center line. So the right half of our body is sort of almost a mirror image of our left hand side of our body. I don't know if it's because of that or whatever, but humans have a tendency to like symmetry to a certain degree. And so you'll see symmetry used in a lot of basic figures. You'll see symmetry used in design elements for things like logos and things like artistic things, artwork. Or you'll see maybe not the whole figure is symmetric, but you'll see elements of symmetry and then a few things that break that symmetry. For example, it's kind of interesting to look at a lot of flags of the different states, the United States, or different countries in the world. And you'll notice certain elements of the flags typically have a lot of different types of symmetries involved. And then there may be some elements that are thrown in there that are not symmetric. So let's look some more here at let's look at some graphing. Okay. So if we clear this all out, and let me get rid of these points here. Okay, and suppose we graph something like y equals x squared. Notice if we replace x by minus x, we know that that's going to have the effect of reflecting over the y-axis. But notice the only points that were fixed are points on the y-axis. In this case, the ones that were in the original graph is just the origin. And yet, even though points were individually moved, collectively they're the same. So we say this has symmetry with respect to the y-axis. Let's look at another example. If we do x squared plus y squared equals, let's see. Let me change this a little bit. Let's change it to. Well, let's do this. There's a unit circle. Now let's do a little stretching on it. So if I replace this by x divided by 4, notice you're going to actually stretch it out 4 horizontally, and let's stretch it up 3 vertically. No, I meant to put divide, not subtract. I don't want to shift, I want to stretch. So now we have this figure here. Notice that this is an ellipse. It has symmetry with respect to both the x and the y-axis. If I change the sign on x, that reflects over the y-axis. All points are removed except these 2 points on the y-axis. They're fixed. But collectively it stays the same. And if I take that and change the sign on the y, I get, well, let me change the sign on y but not x. We get the same figure again. If you do both changes, we're doing 2 reflections, which, as we know, is also a rotation of 180 degrees about the origin. And again, even though points are moved collectively, individually, collectively, they stay the same. So this has symmetry with about the x-axis, the y-axis, and rotational symmetry of pi radians about the origin. Okay. Other figures may have symmetries, but they're not so easy to check out. So let's say we just take a general parabola, like maybe y equals 3x squared minus 4x plus 1. Okay. That also has a vertical axis symmetry, but it's not the y-axis. It's about whatever the vertical line through the vertex there is a line of symmetry. We can have things like, of course, x equals y squared, for example, has a symmetry about the x-axis. we can also look at, let's look at some polar graphing. R equals cosine of 5x, 5t, and let's multiply that by, well, let's just look at that. That gives us a nice little rows, and notice the maximum of cosine is 1, so that's actually bounded by 1. But if I go back here now and multiply this by 6, that's basically replacing r by r divided by 6, everything's going to be expanded away from the origin by a factor of 6. Now notice this figure here, again, let's just get down to this single one here. This has some rotational symmetry as well about the origin. If you rotate this piece, it'll land on this, and so forth. It's the same as the rotation of a regular pentagon. And so there's 1, 2, 3, 4, 5 of those in the all the way around the circle. So that angle of rotation is a rotation of 2 pi over 5. So if I were to replace this by t, say, minus 2 pi over 5, we know that's going to affect a rotation about the origin, and notice it actually turns out to be the same graph again. Now individually, all the points were moved except for the one at the origin stayed the same. All points were moved, so no fixed points except the one at the origin. But what I did is collectively they ended up the same, so this has rotational symmetry. So if I were to now go by, twice this, by 4 pi, we get over 5, we get this. So the original one, this point here, was rotated to here. Now, to go to the pink one, this is the pre-image point. The image point is way over here in the second quadrant. And if I do by, so I need multiples of 2. 2, 4, 6 would be the next one. That's going to be the same, and that's going to take this point here, rotate it all the way down to this one here. And then if I did 8 pi over 5, that's also going to give the same, and that rotates this one all the way around to here. I could get the same thing if I would have just said plus 2 pi over 5. Now it's rotating, but rotating in the other direction, so this one's mapped to here. Okay. Now, a lot of basic figures have some symmetries. For example, an isosceles triangle has one line of symmetry, but no rotational symmetries. Parallelogram, if you look at where the diagonals cross, that's going to be a center of a rotational symmetry, but no lines of symmetry. Kites and isosceles trapezoids have a single line of symmetry. Rectangles have 2 lines of symmetry, and therefore an angle of symmetry about the angle between those 2 lines. Twice the angle. So we're about the center, and then twice the angle. The angle is 90 degrees. So it's 180 degree rotational symmetry. Regular polygons have a high degree of symmetry. So basic questions is what kinds of symmetries do you see here? So let's go down. Actually, let's go down all the way to a degenerate case. If you go all the way down to a single point, then you can any kind of isometry that's going to leave a single point fixed is going to be a type of symmetry. So it's not going to have translational symmetry or glide reflection symmetry, but it will have rotational symmetry of any angle about that single point. It'll also have reflective symmetry about any line through that single point. So that's kind of a degenerate case. We go to a line segment, this is not really a regular polygon, but it does have a line of symmetry. It actually has 2 lines of symmetry. one going that contains that line segment, and then one perpendicular bisector of that has two lines of symmetry, and so that also gives it a 180-degree rotational symmetry, basically the same as the rectangle. Now let's actually get to some actual regular polygons now. So we actually have three sides. Okay, so the question is, what about reflective symmetry? So here's a line. Does it have symmetry with respect to that line? Well, no, because collectively the points did not end up where they started. Can I move the line somewhere? What about if I, let's just show the midpoints. What if I connect up a line going from, say, midpoint to midpoint? Does that give me a symmetry here? No, I don't believe that's going to. That doesn't map up pre-image to image collectively, right? Where could this maybe, oh wait a minute, look there. So there is a line of symmetry. If I go through a midpoint here and then go through the opposite side here. Get that just right. Now what happens? This point here is fixed at vertex 1, but these vertex 2 and 3 swap places basically. So if this is vertex 2 and the original 2' is over here, and if this is vertex 3, then 3' is over here. So there's a line of symmetry. How about another one? Well, because of the way this works, if I can take any vertex to its opposite side, okay, and so in fact all of those lines connecting those up are lines of symmetry. Okay. Now if you get two lines of symmetry about the same, where those two lines intersect, you're going to get a rotational symmetry too, right? Because two reflections equals a rotation. So we should be able to rotate about this same point where these meet, and it would be twice this angle right here. Well, if you look, that angle is 1/6 of pi of 2 pi. In other words, pi over 3. So 1/3 of 2 pi, 2 pi over 3, will be our rotational symmetry about that point. So here's an angle, and there's the center of the rotation is this point X. So, you know, I can't just do any center and rotate it around. I don't get the same figure. Now, of course, if the angle is 0, I can get a rotation. That's the identity with any center I want. Or, of course, I can rotate around 360 degrees any center I want. But anything that's smaller than that, what's it going to take? Well, if you look, if I put it right there, then what angle do I need? I need the angle from here, not to here. Okay, so it doesn't quite, that doesn't match up collectively. But I need it to go all the way to here. Okay, and if I line this up just right, we get a rotation. So it rotates around from here to here. Okay, and so that's rotational symmetry. So in this case, the smallest angle there is well, 120 degrees, or pi over 3. Okay, so what's it going to be if I, let me hide this. So a triangle had 3 lines of symmetry, 3 angles if you count 3 in the identity. So we got the identity transformation, 2 angles of rotation. So not only 120 degrees, but 240, or negative 120 degrees would be the same as going 240 degrees. And so we get 2 angles of rotation, the identity, and then 3 reflections. Of course, no, since this doesn't go on forever, no way this could have any kind of translational symmetry. So what if we increase the sides? So we make a square, a regular quadrilateral, 4-sided polygon. Again, where do I have to put this can I go through with the triangle? We went through a vertex and the midpoint of the opposite side. Or does that work? No. Where do I need to put it to make them work out? Oh, okay, there we go. Opposite vertices, that works. Is there any other possibility? What if I do... There we go, there's another one. So in fact, there are actually 4 lines of symmetry. I'll highlight them. 1, 2, 3. Oops, here we go. Start over again. 1, 2, 3, 4. These are already counted. So 4 lines of symmetry. 1 for every vertex and the opposite vertex, and 1 for every side and the opposite midpoint, like that. Well, if you take the 2 of these that meet at the smallest angle, you double that angle, and you're going to get the smallest angle of rotational symmetry. So we should be able to go at the same center and rotate not to here, but all the way to here. And if I can get it lined up just right, those should grab the right point here. Those should in fact actually line up. Okay, so let me just hide that. So the smallest angle of rotational symmetry there is, in this case, is 90 degrees. Of course, you can also rotate not just 90 degrees or pi over 2, but twice that, rotation of pi, sending vertex 1 down to here. Or we can do 3 times that, 3 pi over 2, which would send vertex 1 all the way around to here. Of course, 3 pi over 2 rotation has the same effect of sending all the points to the same place as if you just did a rotation of minus 90 degrees or minus pi over 2 radians. What if we go up to 5 sides? If you start to see there's a difference in even and odd, there's our midpoints. Lines of symmetry go through a midpoint and an opposite of one side and then the opposite vertex, like that. So in other words, the perpendicular bisector of a side actually goes through a vertex, or a median from a vertex to the midpoint of one of the sides. One of those is going to be perpendicular, and those are the ones that are going to give you lines of symmetry. And of course, if you got multiple lines of symmetry, you're also going to have some rotational symmetries as well. Smallest angle of rotation is from that angle, basically from one vertex to the next. Okay, what happens if we go up to 6? Okay, with 6, we had 6 lines of symmetry and 5 different angles of rotation, plus the identity makes 12 elements altogether in this different symmetries. Okay, and there's 7, 8, 9, 10, and so forth, and you can see what's happening there in general. Now we're going to find out a little bit later that these symmetries of regular polygons turn out to be what we call dihedral groups. They actually form, with the operation being composition, they actually have a group structure, and so these are called dihedral groups. Okay, there's a translation. We can put a formula in here, and then look at some translations of it. This uses some table features that Sketchpad has there. Here we can reflect it over the y-axis, reflect over the x-axis. You can do a horizontal strain, which is a stretch or compression horizontally, vertically stretch it. We can also do a size transformation. Okay, and we'll maybe come back to those a little bit later.